So welcome to today's lesson. We're going to talk about acid-base disorders. We're not going to go over all of the formulas that you need and how to come up with an idea of the acid-base status of a patient. What we're going to talk about more is what's this thing that we commonly refer to as compensation. What is this concept all about? How do we understand if there's compensation in an acid-base disorder? And what if there isn't compensation? What is happening in those situations? So to understand compensation, we're going to take many steps back, and we're going to go to this formula here, which is a very simple representation of what's happening in the blood when you have a lot of acid. So you'll remember this formula from chemistry. This is just the equilibrium reaction for carbonic acid. And we'll use as an example metabolic acidosis. And I chose that example because it's the most common acid-base disturbance that you'll find. So it's probably the situation that we should discuss first. So we'll talk about a metabolic acidosis. And in this case, it will not matter whether there is or is not an anion gap. So we can say plus or minus anion gap. And I want you to know that even though we're talking about compensation in the context of a metabolic acidosis, the concepts that we discuss today will be applicable to all four acid-base scenarios: metabolic acidosis and alkalosis, respiratory acidosis, and alkalosis. So let's begin by erasing the things that we don't need, and let's get rid of this. So now we know it's metabolic acidosis. And so in a metabolic acidosis, what generally happens is you have a drop in your serum bicarbonate. And what you're trying to determine is how far CO2 falls, because that's what you expect. You expect CO2 to drop. Now, why do you expect CO2 to drop? You expect CO2 to drop because of the law of mass action. And that's, of course, taking many steps back to college chemistry. But the law of mass action simply says that in an equilibrium reaction such as this one, if one of the species drops, you're going to move the reaction in a direction to replenish the deficit. In this case, we started with a drop in bicarbonate, and what will happen, according to the law of mass action, is that this entire reaction will predominantly move towards this direction to replenish bicarbonate. In the process of replenishing what you've just lost as a result of having an acid disorder, you're going to drop some species. And the main species that you're going to drop, and the one that you really want to know most about, is CO2. Of course, you'll drop water as well, but because there's so much water in the body, the total body water is about 50 or 60%, this drop is going to be negligible. This drop won't be. So the law of mass action says that as soon as you develop a metabolic acidosis, in this example, you're going to have an immediate drop in CO2. You have to have an immediate drop in CO2. It does not matter what your lungs do or don't do, you must have a fall in CO2. So when you look at acid-base disorders, you can draw a spectrum. And that spectrum is going to have different colors. So let's get some more screen space here. Let's put our reaction back up. So bicarbonate will combine with protons to make carbonic acid, which is a short-lived species, which is why we won't really talk about it so much, but I've included it in the reaction for completeness and accuracy. And in our example, which is a metabolic acidosis, we had a drop in bicarbonate. The law of mass action tells us that this reaction has to move towards the left on your screen to replenish some of this bicarb. In the process, you're going to have a drop in CO2. So let's draw our spectrum. For a metabolic acidosis, this is the color-coded spectrum that we could draw. we're looking at CO2, and so the first thing that happens to CO2 is it drops. And it drops because of the law of mass action. When you have a drop in CO2 because of a metabolic acidosis, that is not what we call compensation. In other words, the lung is not doing anything to cause this drop in CO2. That's because this drop in CO2 is strictly a result of the chemistry, of the chemical reaction that's occurring in the body. If the lung wants to compensate, it's going to have to drop this CO2 even further. And so any additional drop in CO2 is going to come because the lung has exhaled extra CO2. And this is what we call compensation. Now the lung itself could be damaged, or there could be an additional acid-base disturbance. And how would you determine that? Well, the lung will drop CO2 to a certain amount. That's here in the green color. If the CO2 drops even further than that, then you know that something is happening that isn't in control of the lung per se, but that there's some other disease entity that's affecting the lung. And that's called overcompensation, or what we commonly refer to as a second acid-base disturbance. These three colors basically represent the spectrum of what can happen to CO2 in the case of a patient who has a metabolic acidosis. At first, the law of mass action will drop that CO2. That's not a compensatory reaction, that's simply a law of physical chemistry, and that's represented in orange. If you have a healthy lung, then that lung will drop CO2 even further because it's trying to establish a pH where you can live. That's represented in the green. It's what we call compensation. But there are some times or some instances where you not only have a primary metabolic acidosis, but you have a primary problem in your lung, causing you to drop CO2 even further than it should. And that's what we call a second acid-base disturbance. So why do we need to know these? Well, it's a good conceptual spectrum for you to understand what happens in this case to CO2. Now we have formulas. We have actually one formula in particular which will tell us whether we have achieved compensation. And that formula is Winter's formula, so I'll write it out here. So we commonly use Winter's formula to determine what the CO2 should be if your bicarbonate drops. In other words, how low does your CO2 go in order to be considered a compensatory response? And you notice that we have what's here a plus and minus 2, which means we're going to get two values, a value up here and a value here for CO2. If our actual CO2 is outside of this range, then we're in one of two places. Either we're here, where no compensation has occurred for whatever reason, and the drop in CO2 is simply because of chemistry. That's all due to the law of mass action, and we can call that, in other words, acute. Or we're down here, where too much quote-unquote compensation has occurred. The CO2 has dropped well below the lower limit predicted by our formula, and that's because we have a second acid-base disorder. And the last thing that we want to discuss is what happens if the CO2 doesn't drop at all, and it's right here, or increases. Now that's completely incorrect based on the law of mass action. At the minimum, the CO2 has to drop this distance, what's represented in orange, because of the laws of physical chemistry. If the CO2 has actually risen, that means there is another pathologic process that's driving CO2 up. And we're going to call that, again, a second acid-base disorder. So you can see by just knowing one formula, you'll know exactly where you are on this spectrum. Are you in the range of compensation? If you're outside, are you here in what we call an acute area where nothing has changed because your lungs haven't done anything? Or are you down here where too much has changed because you have a second disorder? Or are you up here in the yellow where not only have you not changed your CO2 at all, but you've actually increased it because, again, you have a second disorder? So I like to look at this spectrum when I go through the different types of acid-base disorders. You can use this spectrum for metabolic alkalosis and respiratory acid-base disorders as well. The arrows will change, but the sequence of these events will be the same. And so hopefully that will help you understand what compensation is all about and how we use these formulas to tell ourselves where the patient is on this spectrum. Thank you very much.